Good morning, everyone. Hopefully, everyone had a great holiday weekend, or at least a little time to relax. Today, we're going to get right back at it and jump into the structure of the Earth and plate tectonics. This week will sort of be the last in a series of lectures leading to building up our model of the Earth. As alluded to, we already talked a lot about time and how the planet formed. Now we're going to talk about what it looks like and sort of build upon the other systems related to sustainability and natural disasters and things like that moving forward, such as volcanism, earthquakes, and a variety of other environmental concerns. So we're going to jump right in. I'm going to get into some of the key aspects of the structure of the Earth and generally how plate tectonics work. Some of this might be review from some of you, some of this might be new, so stay tuned. So from a big perspective, as folks were getting interested in how the Earth formed, or how the Earth formed and the age of the Earth, there started to be an increasing curiosity. There's a desire to go out and look around at rocks, look around at rock formations, and figure out how this all occurred. And this really gave birth to the new science of geology. And I'm going to take you through that. Today. So basically, although there had been discussions about certain aspects of this for a long time, there are all sorts of geological stories, and it's very common in literature, in the Bible, for example, and everything. A lot of the stories, a lot of the geological natural hazards are always been evoked as sort of from a higher power. For example, Sodom and Gomorrah, as you might have heard about, thought to be a result of angry gods because of people behaving badly in their view. Was actually related to most likely to meteorite impact. Many other examples like that, earthquakes, volcanism, tied to these things as well. So folks have been around and considering geological principles, certainly in ancient Greek times, Roman times, Middle Ages, and folks had kind of get some idea about geological principles. But in fact, it really wasn't until relatively recent, scientifically, the last 200 years, that it became its own discipline, and where it started to evolve into a field that helped us better understand how the Earth worked. So in some sense, this isn't very different to a lot of the modern sciences. However, what is different is really most biologists, most physicists and chemists, astronomers of the day were always sort of doing some aspect of geology and geosciences, but never really was its own discipline for quite a long time. So by the mid 17th century, people began to become very interested in fossils. Particularly, people would be very interested to find that they could find fossils on top of mountains. And this led to a lot of discussion about how fossils got there, how the Earth worked. Was this whole planet filling up with water and then it all going away? Were there some sort of formation of mountains by geological forces tied to volcanism and earthquakes, things like that? And largely these are fairly controversial. It was not very different than the discussion about the age of the Earth, that there was ideas that for some time were considered heretical, and certainly this was true in terms of saying that water, that the mountains could move, and that the Earth's plates, which weren't even described yet, could move. And at that time, if you think about the historical literature, certainly the religious literature, most people talked about had concepts of great floods. And as a reason, marine fossils that were commonly, formed in the oceans or found on top of mountains were commonly explained in some sort of catastrophic flood scenario. For some perspective, I don't expect you to know this for this class for sure, but one of the interesting things about most of the mountain belts you find, the Rockies, the Andes, the Himalayas, is you'll always find a marine, deposited in the ocean, limestone, which is often very fossil rich, the tops of most mountains, and that's really related to the geological processes of mountain building. We'll talk about very briefly, in some of the lectures later on in the semester. But there's also a major point of discussion. What this led to by about the 1750s is two different sort of viewpoints on the geosciences in the Earth. One was called Neptunism, or who their folks were Neptunists, and those Neptunists thought that all of the Earth's features could be explained by rising and falling of seas. So they believed that things like the mountains, hills, valleys were all features of this old Earth itself. The idea being that the Earth formed. Most of them probably believe the Earth formed by some sort of higher power, and that this episodic flooding of water would carve hills, valleys, and mountains, and leave things like fossils everywhere. And basically that concept has changed only when water sloshed over them during periods of flooding. I think that today most people would agree that this original idea of Neptunism is a bit far-fetched and not really realistic, but there still is a sort of a Neptunist group within the modern geosciences that think about the role that fluids such as the ocean and water, rainwater, snowpack, snowmelt, and precipitation have in terms of percolating into the ground and influencing biological, geochemical, and geophysical processes. So we'll talk about it a little bit as we go through the semester. Neptunism isn't necessarily a well accepted at all in terms of its original interpretation, but of course today there are certain aspects of the role of water, wind, and things like that play that are known to be important and do to some small extent to actually influence the shapes and the evolution of mountains, hills, and other features. The sort of competing theory back at that time, again, mid 18th century, was by Plutonism or by Plutonists. And basically, these are folks who were very attuned to volcanoes, earthquakes, and sort of looked at those big natural processes as evidence for continuous change. And their argument, really back that time was that there was continuously changing of the face of our planet by sort of geological forces that really had nothing to do with seas. Historically, your Neptunists were largely in England and France, where there's not a lot of volcanoes, not a lot of earthquakes, and at the time, a lot of your Plutonists were sort of in Greece, Italy, Southern Europe, and even have been working in other parts of the world, including the U.S., where there was a lot more volcanism. But these groups eventually petered out. Today, we recognize that both geological forces and water and wind forces both play a role. I think today, if one group is closer, probably the Plutonists are a bit closer, but we'll take you through how that evolved through time. So, a lot of the things that led to this, heightened this debate and led to eventually these theories being weeded out, were the fact that there were a lot of awkward questions about where all the water went when it wasn't in flood. How could we have 5 mile high water floods and have any people left on Earth? But of course, there's enough historical storytelling about major flood events and lost cities of the Atlantic and other cities like that people kept the idea alive. One of the questions that was really raised and basically this argument centralized to Europe was that there's enough water to cover the Alps, and where during a period of tranquility, such as the times we live in now, where could all this water go? And that that was explained away by some folks by what we knew very preliminarily about ice caps and the poles and things like that. But really, as we explored and started to get a quantification of some of these things, those ideas sort of went away. So the key thing here is, again, Plutonists believe that there's profound internal forces as well as surface sources, and actually the Plutonists eventually sort of grew more in power and is much more aligned with modern geosciences. Now, James Hutton, who was born in 1726 in Scotland, he's largely considered the father of modern geosciences. He certainly created created and coined the term geology, and he was actually quite an adept reader on both of these arguments, both for the renewal and uplift caused by geological forces that led to the formation of hills and mountains. And he believed there was some cycle to this process, which is aligned much more with the Plutonists. But he also recognized that the oceans, the wind, and precipitation had a role in sort of affecting these cycles. So he was largely credited for a few things, including merging these two concepts. But one of these the key observations he had was he believed that, and it was again considered very controversial, maybe even heretical at the time, that marine fossils and mountaintops were a result of rising mountains, not falling seas, which of course now we know is right. But he also sort of came to this conclusion by doing detailed studies of heat within the Earth, and thought that the heat was sort of the driving engine, just like was happening in the Industrial Revolution at the time, that people were trying to use heat to make more advanced technologies. That was responsible for creating the rocks, the continents, and eventually mountain change, which is fundamental at the time and much more aligned where we're going. So he, by 1785, at the meeting of the Royal Society in Edinburgh, he presented his now fairly famous Huttonian theory of the Earth, with John Playfair, and basically this was all the controversial was seen as sort of one of the first passes in terms of modern geology, and as again has been largely credited for being the father of modern geology. Sorry. So really, we're going to jump forward now. His efforts led to maps that led to some concept of understanding geological time in terms of the units that were deposited on the bottom were older and younger things are deposited on top. He gave birth to the modern geoscience world. But really what I'm going to do for the purpose of this class is kind of skip ahead through some of that sort of the evolution of how the theory evolved, and just jump into how the Earth is actually structured, how it's formed, where we know. Largely, as I alluded to, all the Neptunists, Plutonists, and even Sutton were all working on materials that are very shallow in depth of the Earth, on what we'd call the Earth's surface or the crust, and largely at that time we knew almost nothing. Clearly, by the mid 20th century, the 1950s, we were able to actually make measurements of geochemical things like volcanic rocks, igneous, metamorphic and sedimentary rocks. We were able to have seismic processing to actually look at waveforms and how they transfer to rocks to understand things like the geophysical structure of the Earth. And where I'm going to pick up now is sort of just jumping into the idea of where we know about the general idea of the Earth. So basically, the Earth can be considered to have four sort of main components. There's the inner core. The inner core is about 5,100 kilometers, so 5,000 kilometers, and a radius of about 5,100 kilometers, and it's a solid metal core. It's thought to be largely iron and nickel. There's also an outer core, which is a semi-molten outer core, still largely comprised of iron, nickel, and a minor amount of silicate rocks. Now, the key thing here is that both the liquid and solid core have the same composition, but actually have two forms. So solid inner core, liquid outer core, and the outer core is about just short of 3,000 kilometer radius. So this makes up a fairly large component of the Earth, both by mass and by size. The key things I was going to point out to you here is that above that is basically what's called the mantle. The mantle has I won't test you on this, but is largely lumped into a lower mantle and a upper mantle, or an asthenosphere. So you see this layering. This layering is largely tied to density differences. So most of the core is going to be made of iron, nickel rock. Most of the mantle is going to be made of iron, magnesium, aluminosilicates, or silicate rocks. And as a result, for some clarity as to why the core actually stays together in the solid inner and liquid outer core, is that the density difference between the iron nickel core, even the liquid core, and the aluminosilicate mantle is actually about the same difference as you see between air and a wall. So there's a very, very difficult, very, very large density barrier that causes or prevents really the core from crossing into the mantle boundary. There are some very rare examples where this happens, for minor amounts of the core they're thought to break through, or at least heat up the mantle to create some of the things we'll talk about later. But in general, this is all a slowly convecting, semi-molten, semi-solid aluminosilicate mantle. About 700 kilometers is about the thickness of the asthenosphere. The most of the bulk mantle is about depending on the exact location, ranges to a few thousand kilometers thick. And then the part of the Earth that we live on, as we probably have heard in other geoscience classes, is actually a very thin part of the crust. The Earth's crust ranges only up to about 100 to 130 kilometers thick. The thickest are all under major mountain belts like the Himalayas, for example. And in many cases, near the center of oceans, that crust can be as thin as a few dozens of kilometers, 10 to 30 kilometers. Now, largely speaking here, the mantle can have convection. So basically you can see it slowly heating up. The material can rise to the top of the mantle, and that cycle will continue throughout geological time, quite slowly compared to what we might expect things happen. But one other additional bit of terminology here is that the lithosphere is defined as the crust and the uppermost solid component of the mantle. What's important here is that that sort of solid component of the mantle is the place where the mantles come up by convection, has sort of cooled and crystallized, often with less dense aluminosilicate rocks than the underlying mantle. And that solid or mostly solid upper component of the mantle and the overriding crust basically constitutes what are the plates that can move around on top of this more molten component. So, you know, again, key aspects of the inner core. It's a solid. It's still quite hot, largely iron nickel. So its key things are that it is very dense, and also that it can help create a magnetic field, and creates a very strong center of mass for the Earth. The outer core is more important in actually creating a magnetic field because it's partially molten. But a key aspect of this is, again, that it's going to be iron nickel, and its density difference between that and the mantle is actually much greater than we might expect conceptually. Again, using the analogy of different density between air and a brick wall, for example. The mantle, again, is going to be a largely slowly convecting, partially molten aluminosilicate rocks that are going to basically replenish the crust. So one of the key things about the crust that I forgot to mention is that all the materials we find on our surface today, you know, well, we talked about water and carbon largely being sourced from comets, meteorites, and something called tertiary accumulation of debris in last week's lecture. But almost all the other minerals that are going to be present on the crust are all derived by partial melting or small partial melting of the asthenosphere. So it's actually the volcanism from this asthenosphere and mantle components that lead to partial amounts, partial formation of magma. And that magma transported all the elements, nutrients, and metals that we use for many aspects of modern society, over geological time to the crust. And the crust is where things can be more rapidly recycled by erosion, weathering, and where metamorphism and sedimentary rocks are obviously part of that. So the best analogy, of course, here is that if you think about an orange, the thickness of the orange itself, the thickness of the skin of the orange itself is probably a appropriate analogy for the lithosphere and the crust. You get the sense that even though 130 kilometers is really thick, from compared to, it's a 2-hour drive we're going along the surface, but that gives you a sense of how thick the plates are with respect to everything else, which is actually quite large. The mantle and the core making up the vast majority of the space on Earth. So within this mantle, in addition to basically being the source of the partial melting that brought the minerals, nutrients, metals that we use so commonly to the surface, of course, the bigger aspect that Hutton started to realize back at that time was that this is he hypothesized this is the ultimate source of heat, and that's something we've tested and know quite well now. So within the inner core, the estimates range from about 7,000 to 12,000 degrees Fahrenheit. It's pretty close to that in Celsius actually as well. And that's sort of the heat in the core and the mantle, or what really keeps our planet going and keeps driving plate tectonics, keeps balancing the temperature along with the sun or solar radiation. But dominantly, the three main sources of heat are actually all coming from the core and the mantle. And what I'm going to do now is take you through those three sources of heat. I might have alluded to some of this earlier on in the talking about the formation of the Earth, but the original source of heat, or the first source of heat, is actually called latent heat. This is the heat that was trapped when the Earth formed. I think the modern estimates of this makes about 10% of our heat budget is still the heat that's trapped in the core, dominantly in the core, a little bit in the mantle. It's still trying to get out from the time the Earth formed about 4.56 billion years ago. But the two major sources of heat are actually what's called the heat of crystallization. This is heat that's dissipates from the core into the mantle and is transported by convection with the ascending partially molten magma bodies within the Earth's mantle over time. And when those crystal or that magma gets close to the Earth's surface, at the base of the lithosphere, it can partially crystallize, and even within the mantle start to crystallize, and that's an exothermic reaction that actually releases heat. So it's really in a sense, this heat is largely tied back to this original latent heat, but it's a transport mechanism where it's crystallized as it's released close to the base of the lithosphere and throughout the mantle. The major source of heat we want to consider and think about in terms of driving these Earth processes is actually radioactive decay. Without radioactive decay, we wouldn't be here. The Earth would be a cold mass of rock. Not that's just similar to the background temperatures of the solar system, in the 5-10 Kelvin range. But it's really the decay of uranium, thorium, potassium, all elements that are tied to those radio dating techniques we talked about before, that when they decay, they also give off radiation and heat, and the heat actually flows, from the center of the Earth outwards. Importantly, with all these elements, uranium, thorium, potassium, these are elements that when we talk about these small partial melts from the asthenosphere bringing materials up to form our crust, all of these elements are concentrated, uranium, thorium, potassium are all concentrated in the Earth's crust and actually become really important sources of heat, relatively shallow in within the Earth's structure. So key idea here is with all these sorts of heat, you have heat flowing outwards from the core and the mantle to the crust. That actually sets the balance of our heat budget for the planet Earth, which, if we added a fourth source of heat, of course, trapping of solar radiation and modulating sort of surface temperatures is tied to this. But even in spite of the changes in surface temperatures, even as bad as we get it with climate change, the vast majority of the Earth's heat structure is still going to come from within the Earth's subsurface. Excuse me. So get you a sense of this, so everyone knows what a convection stove looks like, or convection looks like in a pot when you have a gas stove. Maybe if you're camping, you heat it up and you can see these sort of convective cooling cells, or convective cells that bring hot water up and cool and float back down and just continue to do that. So for perspective, that's not at all dissimilar to what's thought to occur in the mantle. It perhaps isn't as homogeneous as we draw it in this picture. It can be much more chaotic, related to structures in the mantle tied to subducting plates and areas that are, there's gravitational thermal anomalies that cause things to be a bit more chaotic. But in general, the same scenario can be thought of as the core trapping enough heat and radiation producing elements in the core that can drive this sort of convection cells within the Earth's mantle. And then it's really, if this analogy might be a bit too far, if you ever cook something like rice pudding, that sort of slowly solidifying crust at the top of the pot, or any type of soup, is actually very analogous to what we're seeing in terms of the thickness, relative thickness, and also the composition of the lithosphere, that solidified upper mantle and the continental crust. So I have a question here. How long can a convection cycle in the Earth's interior take, or how long does it take this loop to take? Does anyone want to take a guess at how long it takes the mantle to sort of do a convection cycle? We don't know this very well, but love to see if anyone can think about the concept of geological time. I'm seeing 144,000 years. That's very specific, but I appreciate the participation. It's probably a bit slow, actually. Sorry, that's probably a bit faster compared to what we're talking. We're a bit slower than that. We don't know exactly, but our best guess is about 1 in every 900 million years a convection cycle is completed. The reality is we know that's wrong. We know there's areas where it happens much more quickly, particularly near mid-ocean ridges, for example. And we know there's areas where it can take much longer, particularly under continents, but that's about the average cycle of when the Earth's material actually, where the Earth's mantle actually cycles through these convection cells. So, trying to build on the concept of long geological times, this is certainly a scenario where these things happen on extraordinarily long times. And for perspective, that lets you know that is that there's probably only thought to be about 4 or 5 life cycles of convection that we're aware of. Of course, obviously going back to this idea of the source of heat, there is much more latent heat early on in the Earth's history. As we had no solidified things and we started to build a crust, that heat would increase. So it's possible we're missing this early evolution of the Earth, just like we're missing some of the early fossil evolution of life and things like that as well. I got a question here: is what information is used to make that prediction? The best approaches that sort of lead to that assumption are something called isochrons, looking at different radioactive decay schemes, radio dating techniques. And basically what happens is if you have a material start evolving with the decay of some isotope over time, if you remelt that, it comes off of another trajectory tied to the amount of mother and daughter nuclides, the uranium and the lead that it decays to, for example. And by everyone sort of looking at the sort of ages of various rock domains we observe on the Earth's crust, the volcanic rocks seem to have a half-life around, different isochrons around that. The other way people use to determine those ages are actually looking at the cycling of water and carbon dioxide through the Earth's history, looking at the relative composition of carbon in for example, the Earth's surface and in the mantle, and that is a similar life cycle, about a half-life of about 1 billion years for carbon cycling. So tied to that, I saw another question here about how often do plate tectonics shift, and that's a little bit more complicated. But and I'm not saying this is exactly right, but it is also tied into that idea of 900 million years, which is that there's been about 6 supercontinents. So there's a little bit of debate about that, but about 6 episodes of supercontinents. So plate tectonics, as we'll get through this lecture probably on Friday, you'll see that the last sort of major cycle of breaking up of the supercontinents about 200 million years ago, and those plate tectonic shifts, are continuously changing today, but are sort of evolving with a half-life of about a few hundred to a billion years, something along those time frames. So going from the structure of the Earth, in terms of looking at the Earth from the core, the mantle, and the crust, what I want to look at now is, of course, going into the part of the Earth we live on. In essence, I just told you it's just the skin of the orange, and it's a relatively inconsequential component. But in reality, for in terms of human population, in terms of thinking about resources we're going to get from the Earth, and also thinking about the hazards we'll have from the Earth that can sort of impact our sustainability, both in terms of not having enough resources or having natural disasters, we really need to focus in on the lithosphere. That's the Earth's crust again, and the solidified upper component, mostly solid component of the mantle. And I think probably all of you know the lithosphere is broken into large pieces called lithospheric plates, or just plates more commonly. And these plates all move relative to each other. There are about 20 plates in reality. Of course, there's 7 continents, 6 major continental plates, as you can see here: the North American plate, South American plate, African, Eurasian, Indo-Australian plate, the Antarctic plate, Pacific plate. But there are a handful of other microplates here, such as the Caribbean, the Juan de Fuca. And I won't go through all these, but you get the sense about 20 plates we need to consider. And I'll ask this question: how do we know where these plates are? We've all probably seen maps of this at some point in the past, but how do we know that there is a plate boundary, surrounding these various different areas? I'll give you an example here. Along the western United States, how do we know there's a plate boundary, running through California? Somebody said earthquakes. Sarah said earthquakes. Of the earthquakes here, and that actually is exactly right. In general, most of what we know about the size, the distribution, and even to some extent the relative motion of the plates is actually tied to geophysical observations of earthquakes. So these can be both actual recorded earthquakes at the surface, or they could be evidence of seismic activity, below the seismic activity, within the Earth's crust that can be managed with earthquake prediction not prediction, but earthquake monitoring with seismographs and things like that. So, largely seismic activity tells us where these things are at, and of course these can be tied also to areas of volcanism in many places. So for those of you saying about the fault line side earthquakes, that's absolutely correct. I got a question here about the directional change of the magnetic field, and that's actually a bit more chaotic. That can change. There's not as much of a predictable cycle, although it does change. So what I'll tell you about that for starters here is that we know, I'll talk this in a slide in a few minutes, what we know is that the magnetic field changes, which is recorded in the magnetic rocks and volcanic rocks. And the way it was originally discovered was basically looking at the Atlantic Ridge and the changing magnetic field of the rocks related to that, it can change on the order of a few dozens of million years or shorter, actually, and sometimes much longer. So we're not entirely sure of a cycle for that, but it does change, and I'll cover that a little bit more as we go along. In terms of these plate boundaries, we alluded to the fact that they're there, but there are three primary types of plate boundaries. And the three primary types of plate boundaries are going to be divergent plate boundaries, where rocks are basically moving apart from each other. Convergent plate boundaries, where rocks are moving towards each other. And transform boundaries, where things are moving side by side, basically parallel to each other. So again, divergent is when boundaries are moving apart. Convergent, they're moving together, and transforms when they're moving along next to each other, sliding past each other. And I'll come back to maps like this in a few different locations, and a few different times throughout the lecture today. But what we're going to talk about, in a reasonable amount of detail, is the fact that how these divergent, convergent, transform boundaries occur have major implications in terms of what resources we'll find there, in terms of what geological hazards we'll expect there, and also sort of the relative size and scope of these issues. So, for the starters here, you'll note that if you want to think conceptually, philosophically about how this whole process gets going, let's go back to that debate of Neptunism, Plutonism. If the heat in the Earth's mantle is going to be the major driver of plate tectonics, the major driver of the evolution of these landforms that we see in the crust, which of these components is going to seem to be most directly involved in providing access for mantle heat to the Earth's crust? In other words, which type of these plate boundaries is going to drive the plate tectonic cycle? Does anyone have a guess? Is it going to be volcanism, basically rising up along divergent plate boundaries? Is it going to be the conveyor belt of plates being pulled down by subduction? Is it going to be transform faults, which are faults again moving past each other rather than colliding into or diverging from? It's when the plates are parallel and just moving past each other. Think about it as driving down a street and hitting a neighbor's car, but being able to keep moving past them. Okay, so someone's mentioning divergent. And clearly, there's a lot of volcanism around divergent plate boundaries. So that's a very good example, or a very good guess, I would say. Does anyone have a counter argument or a different perspective as to which of these types of plate boundaries is most responsible for driving plate tectonics? So I see someone saying subduction and convergent. I like those two guesses, largely because I think everyone left transform, this sliding past each other motion, out of the equation. That's good. So in terms of the folks who said divergent and convergent, those are the two most likely guesses, I think. And it's also an area of contentious debate. Today, what we've come to recognize is that the mantle is hot and convecting under all of the Earth. And the best accepted theory is, in fact, that it's actually the subduction of colder, denser plates around subduction boundaries that can sort of pull mass into the Earth's core and into that subduction boundary. So I think that divergence is a good guess. Clearly, there's a lot of volcanism there when it does release a lot of heat. But the best analogy I've ever heard in terms of how to make the plate tectonics work is thinking about taking a dollar bill and putting it into a vending machine to get a Coke or a candy bar out. Imagine taking that dollar bill and trying to push it into the dollar, into the change machine there. If there wasn't actually little wheels that kept pulling it down. And in fact, the analogy of a dollar bill is not a terrible one. If you think about the relative size and scale of these plates, the density differences, you can almost think of a lithospheric plate as a dollar bill. It's much easier to pull it than it is to push it in. And actually, most people now accept that the density difference is tied to colder, denser rocks being pulled into the mantle by subduction. Is the one that drives the continuation of the plate tectonics. I don't want to get too deeply philosophical about this, but in reality, we know very little about how this process started. Obviously, in order for plate tectonics to get going, you need a continuous source of heat by reactive decay, latent heat, and crystallization that drives the process. There's no doubt about that. But it's entirely unclear to us yet why a certain body of rock would get colder, denser, and start subducting in a controlled fashion. But most people accept that is what started the driving process. The bigger philosophical question, quite frankly, around the plate tectonics and subduction is what substantiates or what perpetuates the process. And most people actually believe now that the existence of water on planet Earth, of free liquid water on planet Earth, is very closely tied to the idea of why plate tectonics can be sustained. Sorry, I mean to say. And the idea there is that as rocks, these cold, dense rocks here in the lithosphere start being subducted, what happens is water, carbon dioxide, and other volatiles in those rocks get heated up as the rock body descends into the mantle, and the devolatilization of water and carbon dioxide causes small degrees of partial melting and some amount of volcanism around these volcanic island or these convergent island arcs, which can be volcanic islands, or they can also be volcanoes like you see in the Andes and the northwestern United States, the Cascades. And most people suggest that it's actually the fact that we have water that can devolatilize and allow things to get more dense as they go. Once those volatiles are lost, the residual rock body gets more and more dense and perpetuates the motion of rock into the subduction zone. So today, most people think that this process is sort of uniquely identified to be perpetuated by the presence of free water in Earth. And for those of you interested in planetary geology, thinking about looking for evidence of life and evidence of planetary evolution that would lead to life on Earth, this idea of substantiating plate tectonics is actually very closely aligned to the creating the sort of ingredients for a sustainable Earth or a sustainable planet body that can withstand life like Earth, I should say. So moving on, I won't sit here and read the table to you, but what I'm going to highlight is the fact that divergent boundaries, where plates are being pulled apart, they're usually oceanic, but there can be continental ones, and I'll talk about that. Key aspect is the two plates move away from one another, and even though that heat that drives the plate tectonic cycle from the Earth's mantle is beneath everywhere, what actually causes most of the volcanism in divergent plate boundaries is the fact that you move away these large points of mass. That creates a low pressure zone under that axis which that mass is removed from. And what happens is it's called adiabatic melting. When that pressure is released, things basically can expand and fill in that area, and then expansion, increasing the volume, decreasing the pressure actually causes the rock to move from a solid to a liquid phase and causes partial melting. Key aspect there is only that spreading, removing pressure helps things melt, and you can see perpetuated volcanism in the divergent plate boundaries. So most of the mid-ocean ridges, like the Atlantic Ridge, we'll talk about more in a minute here, there's perpetuated volcanism there for on the order of about 200 million years, a little bit over that, about 210 million years. And that's largely based on the fact that the plates continue to be pulled apart, creating a mass where, creating a scenario where the mass has been removed from that boundary and allowing the mantle to sort of upwell beneath the boundary and actually lead to melting and sustained volcanism. So these can often be, divergent boundaries can often be very long-lived. They sort of self-perpetuate, largely thought to be by the subduction on the other end of the plate. And major examples, of course, of the Mid-Atlantic Ridge. That's the one I'm going to talk about, mostly in this class. The convergent boundaries are actually where a lot of the fun in geosciences happens. If you want to think about plate tectonics, these can have a lot of different combinations. They can be ocean to continent. So that's where an oceanic plate and a continental plate are crashing into each other. And the key aspect here is that oceanic plates are largely volcanic rocks emitted from the divergent boundaries long ago that moved across and eventually will have the potential to subduct. But really what determines which plate is going to subduct beneath the other is actually density, right? So those volcanic rocks tend to be more dense than sedimentary rocks, and as a result, whenever you see an ocean continental boundary, the more dense rock always goes down. Ocean rocks, for perspective, have a density of about 3.3 kilograms per cubic meter, and that will basically lead to ocean plates subducting below continental plates that have about a density of about 2.7 kilograms per cubic meter. And I won't test you on those numbers by any means, but that gives you a sense that density difference is sufficient enough that oceanic plates will always sort of go down. They'll sink beneath the continental plates. And many mountain ranges are tied to these subduction zones. Common ones are the Andes Mountains, the Cascade Mountains in so the Andes in South America, the Nazca Mountains in South America, the Juan de Fuca subducting beneath the North American plate in the Cascades regions of North America. But this is the most common sort of archetypal convergent plate boundary. The other also common convergent plate boundary is when two oceanic plates meet each other, and this can often be a sort of a battle. It's hard to predict the winner early on. In general, if you think about divergent plate boundaries making the volcanic material, what happens is those rocks get in place at the boundary. They're very hot and buoyant and less dense, and as they cool, they actually will shrink. It's why we call it the Mid-Atlantic Ridge, is because that area actually is a topographical high, and that ridge will get lower topography, decreasing elevation as things move away from the plate boundary. So in general, the rule of thumb is that the older the oceanic plate, the more dense it'll become, and the more dense it is, the more likely it'll sink. And effectively, oceanic convergent plates, whichever one's older will win. And in some cases where they're not very big difference in age, you actually see one subduction plate starting. It'll often sort of break off, and then it'll come back the other way, and you can see this sort of, be quite complicated in ocean settings. But these are important for a lot of the large mountain chains. The Samoan Islands and a lot of the island arcs are Galapagos and stuff like that are often common examples, along with the early evolution of the Himalayas and stuff like that. The Himalayas and stuff like that. So Fiji is a good example. The third example of, sorry, I didn't mean to say Himalayas, I lost my place there. The third example of convergent boundaries is continental-continental collision. And this one is probably the most poorly understood example. The Himalayas, the Eurasian plate are both good examples of this. I'll show you some pictures of this in a second, but in this sense, neither plate's really dense enough to clearly win. And quite frankly, this is an active area of research in my lab working in Tibet to try to determine how India and well, not India and Tibet, but the Indian plate and this Eurasian plate are interacting. And even today, it's still relatively hard to understand how this process goes. But what we do know is these continental collisions can lead to incredibly large mountain belts. The Himalayas has been an example. Another prominent example was the Appalachian Mountains, just to the east of us here in Pennsylvania, from Maine to Georgia, stretching through Pennsylvania and West Virginia, were a continental collision about 270 million years ago, which were a similar process to this. But again, because of in this scenario, we think, we know whichever one's more dense will win, but in both in continental collision, often the density differences are really small, and in essence, you actually just sort of end up getting this very narrow, very high mountain belt that is not very well separated, and as a result can lead to very complex structure in very high mountains. So the last one, again, transform. It doesn't matter if it's ocean-ocean, ocean-continent, or continent-continent, but you typically only see it being ocean-ocean and continent-continent, because even if you're going past each other, the density difference will often cause one to slip below the other. So these are situations where the plates just slide past one another. And the main thing I want to highlight here is that although earthquakes are common in all convergent transform processes, and in fact, in convergent boundaries, you often have relatively few earthquakes, but can be very powerful compared to transform boundaries. Transform boundaries are very prone to having a lot of earthquakes, some very small, some very large, and often these are the ones that I think are more commonly lead to some sort of major catastrophes because of the fact that they're more frequent. People tend to build near them, anticipating a lot of frequent small earthquakes and not recognizing that sometimes there could be a big one. So, out of curiosity, can anyone name an example, other than the San Andreas Fault of one of these big earthquake boundaries? Can anyone think of the major earthquakes in the last, in our lifetimes that have caused major damage, and think about what type of boundary this might fit into? I'll give you an example. We'll use Haiti from, we talked about earlier in the semester. Does anyone know what kind of boundary we've seen near Haiti? So in the absence of anybody wanting to take a stab at that, I will go back a few slides here and just get you oriented. So Haiti is actually right here in between the Caribbean plate and the South American plate, and actually there it's a scenario where you have a transform fault that largely is transform of two oceanic plates sliding past each other. One of the things I wanted to highlight with the transform faults is the fact that you know, the Earth is not, we tend to think of these plates as these blocks, right? We draw these sort of flat surfaces, but remember the Earth's a geoid, right? And that geoid has a curvature, and as a result, the plates sort of have to fit together around these bits sometimes. And a lot of the transform faults are just simply related to the fact we're trying to, you know, almost think of, you know, it's our human construct to have them flat, but in reality they're draped on this geoid, and often they sort of will pass each other in different angles. So what I'm going to do now, before we wrap up here for today, I'm just going to show you a few examples, just give you the scope and scale of some of these transform faults and some of these divergent plate boundaries. What you see here, one of the best examples to see these is a divergent plate boundary, is the Mid-Atlantic Ridge. So notice this extends all the way from the tip of South America all the way up to North America, towards North Pole. And notice that the Mid-Atlantic Ridge will extend all the way along the ocean boundary. But notice that it curves around the boundary between all the different plates. So one of the key aspects we'll get to later in the lecture on Friday is how we can use this information to piece together how plate tectonics theory came to be accepted. So, but notice that this is always a very prominent ridge right along the divergent plate boundary. Okay, so you see that the topography decreases out away from there. That's the cooling of those rocks getting more and more dense and cooling down, removes a lot of the buoyancy. And the ridge, again, is more warm, more buoyant, and has a lot of topography. An example of very common transform faults often offset these divergent plate boundaries. So you'll see that all the way along here, there's a series of transform faults that actually have some relative motion, so where they're sliding past each other along these boundaries. And in all cases, those transform faults can sort of offset the divergent boundary. So someone brought up the age of the Earth. The age and the timing of magnetic reversals. And for perspective, here's the continents, North and South America. This will give you a sense of the age of the rocks, and they're tied to the relative age of the igneous material. So right along the ridge, things are young. As you move away from the ridge, things get progressively older. We know that based upon age dating, but also the way this map is blocked is it actually ties colorations relative to magnetic reversal. So this isn't an actual true magnetic reversal map, but it's sort of imprinted along this information, and you get a sense of how frequently these ages change. And I'll post a magnetic reversal map for everyone's to get a chance to look at. But one of the things that'll give you a sense of here is that even in the Atlantic, which is a relatively old passive margin, the oldest rocks that are coming from a divergent plate boundary are only up to about 200 million years old, just over that in terms of when the Atlantic started going, and when we actually broke up North America from Europe, South America from Africa, and created this divergent plate boundary. So I'm going to just wrap up after these few slides here, but basically, in addition to being major plate boundaries, divergent plate boundaries are important as drivers of life. A lot of folks look at the subaqueous or below the ocean volcanism and divergent plate boundaries as major drivers, a thing called hot smokers, where sulfides, metals, and other components are released by this volcanism, and these can be very important drivers of chemotrophic and life and a lot of biodiversity. And a lot of the theories about how life might have got going on Earth were actually tied back to the evolution of hot smokers around these plate boundaries. So in general, the idea is the fluids emerge from the Earth's material. They're rich in minerals, including a lot of sulfides. They have heat, and basically they create a big temperature boundary compared to the background cooler water, at these vents. And these can be important for generating key components for life, like hydrogen, some abiogenic methane, some other low molecular weight organic molecules, and they play a important role. They clearly host some of the widest, most diverse life forms in narrow areas on Earth. And again, despite no absence of sunlight, no photosynthesis, whatever, These zones can have up to 100,000 organisms in a very discrete area related to this sort of biodiversity. So most, driven by divergent volcanism. So most of the hot smokers and chimneys at boundaries, one of the more famous ones is actually an area called the Lost City Center. That's out in the mid-Atlantic and has been shown to generate incredible diversity, release free hydrogen, actually all of those ingredients we talked about in Stanley Miller and Harold Urey's experiments. Most importantly, this biodiversity creates an area where things higher in the food chain can actually, squids, snails, crabs can come and actually have a smorgasbord of things to chew on. So I won't make too much of a big deal of this beyond this, but divergent boundaries in particular, outside of setting up the sense of how the Earth works, are really important for understanding. Thought to be important for understanding the origins of life on Earth. So the last slide I'm going to show you for today is actually tied to this continental divergent boundaries. Although most divergent boundaries are called mid-ocean ridges or in ocean settings, there's also a very classic and very important example called the East African Rift here. It's called a triple junction where there's the Red Sea, the Gulf of Aden, and then Africa. And this is an area where the continent of Africa is actually being torn asunder by this sort of continental rift environment. There are other divergent boundaries in the United States, in the western U.S., in the Basin Range province between California and the Colorado Plateau or the Rocky Mountain area. So eventually, these will probably end up becoming ocean divergent plate boundaries, and are thought to be an early evolution of that. So on Friday, we'll pick up on the convergent plate boundaries and go through some of the evidence that led people to come to accept plate tectonics theory and the evolution of the Earth's plate as largely driven by plutonic properties rather than Neptunic properties. Logistics for class: we do have a quiz for this week. I kept the quiz not because I wanted it to be hard for you, but because I wanted to make sure you had all the opportunities to see example questions in preparation for the exam next Friday. But I did, in light of the holiday on Monday, I did make the quiz due on Saturday night to give everybody an extra day to do it. I think most of the questions, at least more than half of them, have been covered already in the lecture. Certainly all the rest will be covered directly in the lecture by Friday. And even if you want, you can first look through the slides and be able to wrap it up if you're busy Friday or Saturday. But there is still a quiz for this week. And, largely because I want to make sure you get the questions in time to start preparing for the exam for next Friday. Again, on Friday, we'll pick up with convergent plate boundaries. If anyone has any questions, feel free to shoot me an email, or I'll stay on the Zoom call here for a few minutes. Have a great day, and see you on Friday.